Begin recording. Okay, so we're recording right now. And we're doing a recap of the video lesson that you guys had over the weekend for homework number 11. And I'm recapping pages 3, 4, and 5 of the section 3.2 notes. So here's example 2. In example 2, you're asked to determine if this piecewise function is differentiable at x equals 1. The first thing you always need to do is establish continuity. So that's what I did in the notes here. And establishing continuity is pretty easy. It's 3 conditions, right? Does the point exist at x equals 1? And it does, because x equals 1 is part of the domain here. And I just plug it into 1/3 x plus 2/3, and I get 1. And visually, I see that too. The second condition, does the limit exist? And again, visually, it seems like it does. If I approach 1 from either left side or right side, they're both getting closer and closer to the same value, which is 1. So left and right hand limits are both 1. And to do the left-hand limit, you do the formal notation as you see right here. We got a spotlight out. And when x is approaching 1 from the left side, plug in the x cubed, you get 1. X approaching 1 from the right side, plug into the second expression, 1/3 x plus 2/3, you still get 1. So the limit exists. And the third condition of continuity, does f of 1 equal the limit as x approaches 1? Of course, f of 1 equals 1, the limit's 1, they're the same. So if you're continuous, then you can move on to the next step of determining if there's differentiability. Now, if they're not continuous, stop right there. Call it a day. If you're not continuous, you're not differentiable. We talked about that. You don't need to go any further. You've established, you've answered the question now. But because we're continuous, we gotta peel off another layer and say, okay, let's see what happens if I find left and right hand derivatives. So finding left and right hand derivatives, you don't necessarily need to keep going through finding these derivatives by brute force. You could just say, hey, I know x cubed, I did this in the notes, it's 3x squared. And I'm gonna teach you the shortcuts on Wednesday anyway, which will take just like a second or two to do. Here we talk about when you have linear functions, the derivative is just the slope itself. So it's 1/3. So we see that the derivative, again, the left-hand derivative is at 3x squared. If I plug 1 in, I get 3. That's 1/3 straight up for the right-hand derivative. Plug in whatever you want, you're still 1/3. Those are not the same. Hence, you're not differentiable, because the left and right-hand derivatives do not equal each other. So the derivative x equals 1 does not exist. So that was kind of the key idea from 3.2. Then I talked about ways you can classify situations when you're not differentiable. If you're not continuous, that's it. Just say you're not continuous. And there are a lot of ways you can be not continuous. We talked about jump discontinuities, removable discontinuities, infinite discontinuities. And we should be comfortable with identifying those. Visually, we should. But analytically, if you have a jump discontinuity, the limit doesn't exist, so condition 2 fails. If you have a point discontinuity, removable discontinuity, sometimes they call it point discontinuity, but let's be more formal. If it's a removable discontinuity, f of a exists, the limit as x approaches a exists, but f of a does not equal the limit as x approaches a. The third condition fails. For infinite discontinuities, which are vertical asymptotes, remember that's when true, the limit would not exist, most likely. Also, f of a would not exist, not be part of the domain. But really, what's happening is the fact that the limit's approaching infinity or negative infinity for the one-sided derivatives. Sorry, for the one-sided limits, they're approaching positive or negative infinity for infinite discontinuities. Now, for the other ones, corners, cusps, and vertical tangents, a corner is pretty obvious. Just look at it, right? It's a corner. A cusp kind of looks like this. It's kind of like it's caving in a way. Vertical tangents, if you drew a tangent line at x equals a here, it would be straight up vertical. So that's also happening. And ways of classifying it, ways of analytically determining it, I did talk about that in the video, so you don't see it here. But if you have, so again, in each case, the LHC does not equal, well, actually, I lied. The LHC does equal the RHD here. But they're both positive infinity or they're both negative infinity. Like see here, if I get closer to A on the other side of A, that's a positive slope and very steep. Or here, they're both negative slopes and very steep. For the corner, the LHD does not equal the RHD. and they're finite, meaning they're actually numbers you can solve for. Like maybe this is the slope here is at -2, and maybe here it's at like 1. So they're finite values, but they're not the same. Here, they're not finite, they're infinite values. So like as I'm approaching a here, my left-hand derivative does not equal my right-hand derivative, and they're going to be either negative infinity, positive infinity, or it could be the other way around, positive infinity and negative infinity. So a little different than the vertical tangent, where they're both positive, they're both negative infinity. So that's how you can, pun intended, differentiate among these different classifications for differentiability. I know I use differentiate in a different way, right? It has a multiple meaning. And that was pure organic, just so you know. But anyway, I just made that up. Let's keep moving. So that was the classifications. And then you're asked to do that for this one here. And this one, I believe, was a corner, if I'm not mistaken. And the way I was able to, first of all, it was continuous. It was a piecewise function. And I think there was a corner at x equals 0. Yeah, at x equals 0. We're going to do more of this and get into this a little more detail later today. But that was a recap. And if we go to the Google form, yes, contrapause is when you reverse the statements and negate. So like if the Foreigners win on Sunday, I am happy. Yeah, so that's my favorite football team. I've followed them since the mid '80s. Now, if you reverse it, if I'm not happy, that's because the Foreigners did not win, and that's very true too. I was not happy yesterday afternoon, so that's how that works. So it should be putting my name first, and then negating that statement, and then the hypothetical now becomes a conclusion, and of course you negate that as well. Yeah, I made a mistake on that one. I accidentally said they're both positive and negative infinity. That was just a total brain freeze there. So that's my fault. So I'm glad you guys caught that. They're actually gonna have different signs of infinity. That's what they're supposed to have for the left and right hand derivatives of a cusp. Describe differences among the following. Yeah, so just want to kind of see what you guys are saying here. I just described that in the last 2 minutes, right? Yeah, equal finite numbers. This is a good one. It's not differentiable. Does not equal positive infinity, negative infinity. Good. Vertical tangent, but undefined values. This is a great description there. So very good work. Whoever that was, give kudos to that person. It's probably was Ryan. You look like you're the first one to submit. So I'll have to look a little more detail, but that's really good explanation. Here, let's assume the left-hand derivative is -2, while the right-hand derivative is positive infinity. That one is kind of interesting. I would actually say it's not differentiable because of a discontinuity. Now, you're tempted to say, and it's good. I'm glad 91.5% said green. There's a couple that said orange. Yeah, vertical tangent. I mean, yes, when you have a vertical asymptote, that, right. I mean, the slope of the tangent line on one side is definitely going to be approaching positive or negative infinity if you have a vertical asymptote. Definitely not a cusp, and definitely not a corner, because it's not continuous. Corners are, I think the big thing here is you don't have you're not continuous. See, in order for these things to happen, these are like 2, 3, 4 are all continuous. 2, 3, 4 are all continuous. The situation I described here is not continuous, and that's why you're not differentiable. So you're not going to have vertical tangents. Vertical tangents are continuous functions. Likewise the cusps and corners. So if you have something like this here, and you could do a piecewise function like this. That's totally legitimate. I could totally make a piecewise function like that. I could say f of x equals, I don't know, -2x plus 4. Let's say that's like a 2 there, when x is less than 2 or less than or equal to. And then I could do like 1 over x minus 2. I just made that up, and that actually satisfies that. And that's not continuous because the left-hand limit does not equal the right-hand limit. Even though it's defined x equals 2, but the limit does not exist here, you're not continuous. You're not continuous, you're not differentiable. So it's just kind of a thinking problem there. And then this one here, why are the two statements below not true? Yeah, like you could be continuous like a corner, but not be differentiable. Or a function is differentiable will be continuous. Actually, hold on a sec. Hold on. If you are differentiable, you are continuous. What was I talking about there? I think I meant to say if you're not differentiable, you're not continuous. Okay, wow. I apologize if I confused you guys about that one. That was really bad. Yeah, a function that is differentiable x will be. That is a true statement, actually. Yeah, I apologize. I meant to say if it's not differentiable. Okay, hopefully, yikes. Let me maybe fix that for those who are still gonna maybe submit this. My apologies. What I meant to say, if you're not differentiable, yeah, like for example, like a cusp, you're not differentiable, you are continuous there. Which is the same thing saying if you're continuous and differentiable, that's not true because like a vertical tangent is continuous but not differentiable. Let me just close that. Did I just lose you guys? Okay, wow, that was weird. Okay, hopefully I'm still recording. That's really, really weird. Okay. Okay, I think we're good now. No wonder it was a little hiccup. Okay, so anyway, that's a recap. All right, so I'm gonna stop the recording.